Guys, my name is IBM and I would like to take you to the last lesson or the last part of astrophysics and cosmology. Do not forget to download these videos. Do not forget to share. You can write your comment. You can ask any question. I don't care whatever comment you write. I don't really mind. I can always answer your questions. So do not forget that this is the Cambridge International Education Curriculum. So here I am to take you through the last part of astrophysics and cosmology. By now you should be asking yourself what is the difference between astrophysics and cosmology. Of course, in astrophysics we were talking about we're looking at objects in space. We were studying distances of objects in space, and therefore it's like astrophysics is concerned with studying objects in space. That's why we call it astrophysics, coming from astronomical, and astronomical refers to objects in space. On the other hand, when we talk about cosmology, we shall be actually referring to the origin, cosmos, origin of the universe. How did it start? That is what cosmology is concerned about. So this is lesson 3. And without wasting time, I want us to go to the last part, which is cosmology. So I would just like to take you through cosmology and emission spectrum to start with, because in cosmology, we are concerned with explaining what we believe must be responsible for the creation of the universe. Of course, there are several theories. There are several theories that explain the origin of the universe, but one of them is what we are going to cover in cosmology. The other theory is the creationist theory, according to the Bible. For the Christians, is also in existence. There's also the theory of evolution, according to biology, and so on and so forth. So one of the theories that explain the origin of the universe will briefly be explored in this unit. If you're doing OCR, you may go into deep details of the theory we are going to talk about here. But for those doing Cambridge, you don't need to go into the deep details of. You don't need to go deep into details of the origin of the universe according to the theory we are going to explore here. So cosmology is concerned with the origin of the universe. So astronomers are very limited in how they can investigate objects in the space. For example, measuring distances of all those objects. Basically, they rely on light which is emitted from the stars. So all the techniques used involve analyzing the light emitted from the star or the galaxy. That's why in the first parts, or in lesson 1 and 2, we were actually relying on the light from distant galaxies, or we're relying on electromagnetic radiations from distant stars to be able to determine their distance from the Earth. So all the techniques used involve analyzing the light which is emitted from the star or from the galaxy, or light which is coming from the galaxies. Of course, these stars are in these galaxies. So what is special about the light from those galaxies? The most important technique used here is analyzing what we call the emission and absorption spectra of stars. Now, in quantum physics, you must have mentioned emission and absorption spectra, or you will mention emission and absorption spectra if you have not covered quantum physics. But what do we mean by emission and absorption spectra? So light from distant galaxies, when analyzed using a very powerful telescope, it does not appear as a continuous spectrum, because As light travels through space, it passes through cooler layers of gas, such as hydrogen. And as light travels through cooler layers of gas, some photons of light are always absorbed. And if those photons are absorbed, it means those wavelengths, of course, each photon, as mentioned in quantum physics, each photon corresponds to a wavelength. I will need a pen here. So in quantum physics, you will see, or you must have seen, that the energy of a photon is equal to hf, which is equal to hc divided by the wavelength, meaning that each photon corresponds to a wavelength. So light from distant stars, as travels, before it reaches us, it passes through cooler layers of gas. So some of the photons may be absorbed. Those absorbed photons may not appear to be seen in the spectrum when an observer looks at the spectrum. Those lines may appear as dark. Those wavelengths may appear as darker lines when the observer looks at the spectrum. So the position of the missing photons or the missing wavelengths would be uh, the positions where we find the dark lines, and that would be what we call the absorption spectrum. Of course, the line spectra, where the absorption spectra are, is where we expect the line emission spectra to be if those photons were re-emitted. So the absorption spectra would be darker lines if the light falls onto um, dark lines if the light falls onto a white background, for example. Then the emission spectra would be bright lines if the light is falling onto a dark background. So these photons, whose energy is enough to promote electrons to higher energy levels, are always absorbed and will not continue on their way to be observed by the observer. So this will result into either emission lines or emission spectra, which will be bright lines on a darker background, or the absorption spectra, which will be darker lines on the bright background, as you will see in quantum physics. So astronomers are going to concentrate on analyzing these lines, either the dark lines or the bright lines, which we are going to call spectra, or the spectral lines of stars. So I'm saying light from a different distant star. Instead of being the 7 colors ranging from red to violet, within the 7 colors you may find darker lines. These lines are the ones we are going to call the spectra. So these lines correspond to wavelengths which have either been absorbed by electrons to be promoted to higher energy levels in atoms of gases or cooler layers of gases, so that they do not appear as wavelengths, but instead they are just going to appear as darker lines on a bright screen or on a white background. So astronomers will now just study these lines and compare with them with what is observed in the laboratory, to rely on this to be able to analyze or to be able to investigate objects in space, such as distant galaxies. So more details on this, more details on that will be found in quantum physics. More details on emission and absorption spectra will be found in quantum physics. So in stars, we know that we have predominantly it is hydrogen and helium. These are the sources of fuel that are used by these stars to generate their own heat and light. And this hydrogen, or the hydrogen and helium, may absorb some of the emitted light wavelengths without allowing it to travel towards the observer to the Earth's surface. So the cooler layers of hydrogen and helium surrounding the star may absorb some of these photons. And I said each photon corresponds to a wavelength. If that photon is absorbed and does not continue on its way to an observer, then the observer will see a darker line corresponding to the position where that photon is supposed to be. That is what we mean by the emission. The emission and absorption spectrum. Basically, it is the absorption spectrum. Therefore, characteristic lines are present in a spectrum. Characteristic lines are present when the spectrum is analyzed. Those lines are the ones I'm calling dark lines for an absorption spectrum, and they will be called they will be bright lines for an emission spectrum. When astronomers observe light from distant galaxies, they observe differences in the spectral lines to the light from the sun. So it's like there is a difference. If you observe the dark lines, for example, in light coming from distant galaxies, and compare with the dark lines in light coming from, say, the sun, which is our star, or the star in the Milky Way galaxy, it's like there is a difference. So these lines are very important because the lines have the same characteristic pattern, meaning that the element can still be easily identified by astronomers. They just appear to be shifted slightly. So if we have, for example, 5 lines for light coming from a certain galaxy, and we have 5 lines for light coming from stars, it's like they have the same pattern, only that you may find that the lines coming from a distant galaxy could be shifted slightly to one end. And to which end are these lines shifted? And why are they shifted? So astronomers are going to rely on that fact to explain the origin of the universe. So the lines have the same characteristic, which means the light is passing through the same material. Light is passing through the same, say, hydrogen and helium, because all stars are surrounded by hydrogen or helium. They're surrounded by cooler layers of hydrogen and helium, which means the lines are going to be almost similar. The only difference would be that uh, lines observed in light coming from a different star or a different galaxy could be shifted or slightly shifted to one end of the spectrum, which we are going to call the visible spectrum. Our task would be to explain why are they shifted. So if you recall, so the lines have the same characteristic pattern because the light is passing through the same chemical, which could be hydrogen or helium. But like we are saying, they are slightly shifted. And these lines actually appear to be shifted towards the longer end, or towards the red end of the visual spectrum. And because red corresponds to the longest wavelength, it's like they are already shifted, as we shall mention later on. And therefore, these lines are actually indicating an increase in wavelength of light, as we shall mention later on. So the lines are tending to move towards the red end of the visual spectrum as time goes on. So because they are moving towards the red end of the visual spectrum, from Richard of York gave birth in vain. Red corresponds to the longest wavelength, which is around 700 nanometers, and violet corresponds to the shortest wavelength, which is about 400 nanometers. However, in the visible spectrum, red and blue are the most significant, or the most significant colors in this spectrum. So the spectral lines of light, or the spectral lines in light coming from distant galaxies, has been observed to be shifting towards the red end. In other words, the darker lines, if they are darker lines seen in the visible spectrum, are turning towards the red end of the visual spectrum, or are turning towards the red end of a continuous spectrum. And therefore, because red corresponds to the longest wavelength, we can therefore believe that maybe the wavelength of light is increasing as it travels a longer and longer distance every time. So in other words, in cosmology, we should be able to explore the origin of the universe in space. We should be able to explore the Doppler redshift, where we have said the spectral lines are indicating that the wavelength is increasing. Therefore, uh, we call that the Doppler redshift. If you recall the meaning of the word Doppler, in AS physics, that is in waves, you talked about Doppler effect, where there was an apparent change in the frequency of sound because there was relative motion between the source and the observer. So on Earth, we are very familiar with the Doppler effect of sound, which could easily be seen or observed when sound waves move past an observer, or when a source of wave a source of sound moves past or away from an observer, we could notice that the frequency would increase if the source of sound was moving towards the observer, and the frequency would decrease if the source of wave was moving away from the observer. But of course, in space, the Doppler effect of light is the most pronounced here. So the Doppler effect of light can be observed when we look at spectral lines um, in light from distant stars. And experiments show or observations show that the spectral lines are turning towards one end of the visible spectrum that we are going to call the Doppler redshift. So it is just an apparent change in wavelength or frequency, that is the Doppler redshift. But of course, because wavelength is inversely proportional to frequency, an increase in wavelength means a decrease in frequency. So that is what we are going to call the Doppler redshift. Then we also have the blue shift. Of course, it is just the opposite. Okay, so because Doppler effect could be Doppler redshift, it could be Doppler blue shift. I said in the visible spectrum, it's red and blue which stand out. The red and blue colors stand out most. So that's why we shall be talking about the Doppler redshift, and the opposite will be the blue shift. So the Doppler redshift will be referring to moving away because the wavelength is going to be increasing, just like when a sound source approaches you, the frequency increases, which means the wavelength decreases as it approaches towards you. So for the Doppler redshift, the wavelength is actually increasing. It is turning to the red end of the visible spectrum. So if the wavelength is increasing, it's simply because the frequency is decreasing, and the frequency decreases when the source is moving away. So the difference between the two would be redshift will be redshift will be away from the observer, and then the blue shift will be towards the observer. So we shall define the Doppler redshift or the cosmological redshift as the fractional increase in wavelength. The wavelength actually increases when I refer to the redshift. And of course, wavelength is inversely proportional to frequency, so it can also mean the decrease in frequency due to the source and the observer receding. The word receding means moving away from each other. So the reason as to why astronomers are observing the spectral lines found in light which is coming from distant galaxies to be shifting towards the red end of the visible spectrum is possibly because the wavelength of light is actually increasing. And if the wavelength of light is increasing, what is really happening? Astronomers argue that the space between the source of light and the observer is actually expanding. Maybe the universe is expanding, that's why light is traveling a longer and longer distance every day. That's what we are going to call the Doppler red shift. So in the exam, I want you to be very sure that you should emphasize redshift, referring to the wavelength of the spectral lines. It's the wavelength of the spectral lines which increases towards the red end of the visible spectrum. It's the wavelength of these spectral lines which increases towards the red end of the visible spectrum. A layman and someone who is not really prepared may think the spectral lines are becoming red, or that they will think the wavelength is becoming red, but we are saying the wavelength of the spectral lines is increasing, and therefore it is turning towards the longer wavelength, or the longest wavelength in the visible spectrum, which is actually the wavelength of red. That's what we are going to call the Doppler redshift. Okay. So just to take you further to explore and understand what we mean by the Doppler redshift, I referred you to what you mentioned in AS, that is Doppler effect. Recall that the Doppler effect is the apparent change in wavelength or frequency of the radiation from a source due to its relative motion away from or towards the observer. And I say, to be specific, if it is towards the observer, we shall call it the Doppler blue shift if it is towards the observer. But if it is away from the observer, we shall call it the Doppler redshift. On Earth, the Doppler effect of sound can be easily observed when sound waves move past an observer at a notable speed. We always experience this when an ambulance approaches us and when it moves away from us. When it approaches us, we notice a high frequency, which is equivalent to noticing a decrease in wavelength. And when the ambulance passes us, we notice a low frequency, which is equivalent to an increase in wavelength. So away is associated with increase in wavelength, and towards is associated with a decrease in wavelength. So in space, the Doppler effect of light can be observed when spectra, those are the spectral lines I've been talking about, when spectra of distant stars and galaxies are observed. And we are saying this is known as the redshift. So redshift is known as the redshift if the object is moving away. So the reason as to why astronomers argue that the universe is expanding, as we shall see later on, is because of this redshift. Why is there a redshift? Why are the spectral lines observed in light from distant galaxies tending towards the red end of the visible spectrum? Why is the wavelength tending towards the red end of the visible spectrum? Perhaps it's because the space between the source and the observer is increasing. But if it wasn't increasing, maybe you would call it a blue shift. If the object was moving towards the observer, then we would call it a blue shift. But since we don't experience a blue shift, then the universe could be expanding. The galaxies and the sources of light, or the stars, must be moving away from the observer. So this takes us to what we call the Doppler redshift equation, or the Doppler redshift formula. So for non-relativistic galaxies, Doppler redshift can be calculated from a formula which is delta lambda over lambda is equal to delta f over f, which is v over c. This formula is given in the list of formulae. You will always find it in the list of formula. Delta lambda is a shift in wavelength, or a change in the wavelength, or a difference in wavelength, which is the wavelength observed when looking at light from distant galaxies minus the wavelength of the spectral lines when measured in the laboratory. So that difference is what we call the shift in wavelength. Then lambda is of course wavelength emitted from the source. Delta F is the shift in the frequency. Of course, if there is an increase in wavelength, we expect a decrease in frequency. F is the frequency. V is the speed of recession. Because we are talking about a Doppler redshift, recession means to recede is to move away. So it is the speed with which a galaxy or a star is moving away. So that's what we mean by the V here in this formula. So it's the speed with which the galaxy is moving away from the observer. Then of course we know that c is the speed of light. So this is what we call the Doppler equation. It's what we call the Doppler equation. Okay, so in an exam we should be able to use this expression here for calculations, and I'm saying it is always given in the list of the list of formula. So astronomers and cosmologists often assign a value for the term redshift. For example, if a galaxy shows a redshift of 8%, what does that mean? This means that the ratio delta lambda over lambda, or delta f over f, or v over c is actually 8%, which is the same as 0.08. So that is what we call the redshift. So I can say the redshift is 8%. What does that mean? That fraction delta lambda, the change in wavelength over the normal wavelength in the laboratory is 0.08, or the change in frequency over the normal frequency in the laboratory is 0.08, or the speed of the galaxy compared to the speed of light is 0.08. That's what we mean by that statement. Assigning a value, assigning a value for the term redshift. Question, and this is a very important question. How are cosmologists able to determine that light from a distant star has undergone redshift? So I said astronomers and cosmologists look at light and analyze the spectral lines. So the spectral lines correspond to certain wavelengths which have been either absorbed or re-emitted. And by analyzing these spectral lines, if they compare the spectral lines seen from light or seen in light coming from distant galaxy and compare with the spectral lines seen in light as observed in the laboratory, of course for the same chemicals, because if we know that light from a star is passing through hydrogen, then we can pass a continuous beam of light through hydrogen in the laboratory and we see the position of these spectral lines. So if we compare the two observations, we can now come to a conclusion that either the spectral lines are shifting towards the red end of the visible spectrum. So cosmologists are going to simply examine the lines or the so-called spectral lines. They will examine the lines in the spectrum of light from the star and they will compare. By comparing the wavelengths of the spectral lines of light from the stars with the known values, in the laboratory, astronomers can determine that light has undergone what we call a redshift. So if in the laboratory, we know that if this is the continuous spectrum ranging from red to violet, and we know that the position of the lines, let's say passing through hydrogen, are these three lines seen in hydrogen. Then if we observe light coming from a distant galaxy and we notice that the position of these lines has been shifted slightly towards the red end of the visible spectrum. This is the red end, that is the violet. So it's like now these are falling into longer wavelengths. So by comparing this with this, astronomers will come to a conclusion that light has undergone what we call a red shift, or it has been red shifted. So that is how astronomers and cosmologists are able to determine that light from a distant star has undergone redshift. They just examine the spectral lines of light from the star and then compare these spectral lines with their known values in the laboratory. And then they can determine that light has been redshifted. Examples. Number one, the spectral line, the spectra, of course, spectra is plural. The spectra shows dark absorption lines against a continuous visible spectrum. So we have dark lines on a visible spectrum, that is a range of 7 colors as shown in that diagram. A particular line in the spectrum of light from a source in the laboratory has a frequency of this. So this is in the laboratory. The same line in the spectrum of light from a distant galaxy, so this is from a distant galaxy, has this frequency here. What is the speed of the galaxy? What is the distant galaxy? What speed is the distant galaxy moving in relation to the Earth? Is it moving towards or away from the Earth? So let's compare the frequencies first. The frequency of these spectral lines, we note that in the laboratory, the frequency is actually 4.570 times 10 to the power 14 hertz, which is actually higher than what we are seeing for a distant galaxy. It is 5.547. So if the frequency, remember frequency is inversely proportional to wavelength. So if the frequency in the laboratory is high, it means the wavelength in the laboratory is low. And if the wavelength is lower, the frequency of light from a distant galaxy is lower, which means the wavelength is actually higher. So this is a higher wavelength, this is a lower wavelength. So we can now believe that there has been a red shift. There has been a red shift. So If there is a redshift, that is only because the galaxy is moving away from the observer or from the Earth. So let's find the speed. So using the Doppler redshift equation, we know that delta lambda over the wavelength in the laboratory is equal to the difference, the shift in frequency over the frequency in the laboratory, which is going to be equal to V divided by C. So we want to find V and C, and they have given us this part here. So I'll use that part and I make V the subject. So V is going to be equal to a change in F over F times C. So the change in wavelength, the change in F is going to be the difference between those two. So I'll say 4.570 minus 4.547, and I will multiply this by 10 to the power of 14. Then I will divide this by the frequency in the laboratory, not the frequency of the from a distant galaxy. It is always, we compare with what the known values are, those ones in the laboratory. So this is divided by 4.570 times 10 to the power of 14. Of course, I'm going to multiply this by the speed of light, which is 3 times 10 to the power of 8. So I have to check with my calculator. So 4.57 minus 4.57547 divide by 4.57 times 3 exponent 8. So this is giving me 1.5 times 10 to the power of 6. Meters per second. So this is the speed of the galaxy, and we are saying because the observed frequency is less than the known frequency in the laboratory, it means, and frequency is inversely proportional to wavelength. So it means the observed wavelength is more than the wavelength in the laboratory. So we conclude that it is already what? Already shifted, or it is moving away. So it is the galaxy is moving away from, because the spectral lines are already shifted, then the galaxy is moving away from the Earth, or is moving away from the observer. So you notice that when you look at the diagram, it shows that all the spectral lines have been shifted towards the left-hand side, which means the galaxy is moving away from the observer. Okay. Example number 2. So the galaxy is moving away. The observed wavelength of spectral lines is turning to the red end of the visible spectrum. So the wavelength of the spectral lines is turning to the red end of the visible spectrum. Example number 2. In the laboratory, an emission spectral line is observed at a wavelength of 656.4 nanometers. The same spectral line in the spectrum from a distant galaxy has a wavelength 663.1 nanometers. Determine the speed of the galaxy. So in the laboratory, this is the known value. Of course, in the laboratory, it is always the known value. But this is what is actually observed. If we analyze spectral lines for distant galaxies, so what is the speed? So remember the Doppler equation, it is always given the list of formula. Delta F over F is delta lambda over lambda, which is the same as V divided by C. I need to increase the thickness of this pen. I don't see thickness here. Okay, so making V the subject, I have that V Making V the subject, I have that V is going to be equal to, because they have given us wavelength, I'll only take this part of the equation. So V is going to be equal to delta lambda divided by lambda times C. So this is going to be 663.1 minus 656.4 divided by the wavelength in the laboratory is the known wavelength. So this is going to be 656.4. Then I'll multiply this by the speed of light, 3 times 10 to the power of 8. So of course, I know that the units nanometers will cancel out. That's why I'm not bothered with them. So I'll just check my calculator. 663.1 minus 656.4 divided by 656.4 times 3 exponent 8. So this is giving me 3.1 times 10 to the power of, it's times 10 to the power of 6 meters per second. So this is the speed of the galaxy. Of course, the observed wavelength is higher than the wavelength in the laboratory, so we can conclude that it is moving away because it is already shifted. The wavelength is tending to the red end of the visible spectrum, so that is, it is already shifted. Okay, let's see if we have more examples. Number 3. A galaxy has a rotational speed of 9,400 kilometers per second. Calculate the fractional change in the wavelength of the observed spectrum. Fractional change. Okay. So we know that from the Doppler redshift, I think there is part B. Okay. So for part A, from the Doppler redshift, we want the fractional change in wavelength. We know that delta F over F is equal to delta wavelength, change in wavelength over the known wavelength in the laboratory, which is equal to V divided by C. So I'll take this part here. So I want the fractional change. I want this change here. That is the fraction I'm looking for. And it's going to be V, which is 9,400. It's kilometers, so I'll say times 10 to the power of 3. Change it to meters per second, then divide by the speed c of light, which is 3, times 10 to the power of 8. So this is going to be the fractional change. So I'll say 9,400 exponent 3 divided by 3 exponent 8. So this is going to be 0.031 to two significant figures. If I want this as a percentage, I'll multiply this by 100 times 100. So this is the same as 3.1%. So the fractional change is 3.1%. Then part B. Part B, the fractional change in the wavelength of the observed light from a galaxy is 0.1, which is the same as 15%, or we say its redshift is 15%. Whenever they tell you the redshift is this, so that means that is the fractional change in either wavelength or in frequency. So calculate its rotational speed, state an assumption made. So let's just calculate the rotational speed here for part B. So we have that the fractional change in wavelength is equal to V over C, and they've given us the fractional change as 0.15 should be equal to V divided by C, which is 3 times 10 to the power of 8. So it means if I make V the subject, V is going to be 0.15 times 3 times 10 to the power of 8. I'll just press my calculator. 0.15 times 3 exponent 8. So this is 4.5 times 10 to the power of 367 power 7 meters per second. So what assumption can we make? We can assume that the recessional speed has remained constant ever since this started happening. Okay, so let's talk about the expanding universe. So the consequence of this redshift is that the universe can be considered to be expanding as argued by cosmologists. Because if the universe is not expanding, then why is the wavelength of the spectral lines redshifted? So if the universe was not to be expanding, we would not expect the wavelength of the spectral lines to be redshifted. So we now agree that the universe is expanding because of this Doppler redshift that was discovered by cosmologists. So let's understand the expanding universe. So after the discovery of the Doppler redshift, which we have just explored, which argues that the wavelength of the spectral lines attain towards the red end of the visible spectrum, astronomers and cosmologists began to realize that almost all galaxies in the universe are receding. And if all galaxies in the universe are receding, then we can argue that the space between the Earth and the galaxies must be expanding. It's like the space between all objects in the universe is increasing. So this expansion stretches out the light waves as they travel through space, shifting them towards the red end of the spectrum. So it's this expansion which we are talking about that is responsible for the redshift. Because the space between the galaxy and the Earth, or the space between the galaxies, is increasing, then the light from the stars is being stretched out to a longer distance. This also relates to what we observe every day. When you wake up in the morning and you see that the sun is rising and is appearing red, it doesn't mean that it is that the seven other colors, the other six colors are not visible in the light, or they are not in that light. It's only because during sunrise and sunset, light travels through a longer distance. And because the red corresponds to the longest wavelength, we are able to see red reaching us during sunrise and sunset. So the expansion of the space between the galaxies is maybe stretching out light through a further and further distance every day. That's why the wavelength of the spectral lines is tending towards the red end of the visible spectrum. So we can simply say that the more redshifted the light from a galaxy is, the faster the galaxy is moving away from the Earth. To be specific, the more redshifted the wavelength, the wavelength of the light from a galaxy is, the faster the galaxy is moving away from the Earth. Because why would the spectral lines be more redshifted if the galaxy was not moving at a faster speed from us, or from the Earth as a reference point? And the best way to visualize the expansion of the universe is we shall compare it to uh, stars which have been placed onto an inflating balloon. And as the balloon expands, the stars move further apart. The stars themselves actually do not move, but the space between them is stretching out. So they appear as if they are moving away from each other, yet it is the space between them which is being stretched. So I demonstrated this using this simple animation here. So here we have a simple situation where we have the universe has not yet started expanding, and we look at the stars. And the second diagram shows the space between the stars having increased because the universe is expanding in all directions. So the space is stretching out in all directions. And if you compare with the third diagram, notice that the space between the stars has uniformly increased in all directions. So this is what we mean by the expanding universe. So just like the stars on the balloon, The galaxies are moving away from each other. However, the stars themselves do not move. But because they are in galaxies which are moving away from each other, since the space between them is increasing, then we can predict that the universe is actually expanding. So I try to demonstrate this with a simpler animation here, where I try to inflate a balloon with a pressure pump here, with the stars marked on the balloon. And we notice, of course, the stars themselves are not moving, but the balloon is expanding. And as the balloon expands, we notice that the space between the stars is actually increasing. And if you observe this very carefully, you notice that if the space is increasing, then the universe is also going to be behaving the same way. And that is actually what we call the expanding universe. So it is actually a space between the galaxies that is expanding. The galaxies themselves may not also be moving, but because the space between them is expanding, then we sometimes say they are actually moving away from each other. The universe is expanding. And if it is expanding, then why is it expanding? When did it start to expand? This now takes us to what we call the Big Bang Theory and Hubble's law. If the space between galaxies is expanding, because this has been verified by the Doppler redshift, why is the space between the galaxies expanding? Until when will it expand? When did it start to expand? This takes us to what we call Hubble's law. Edwin Hubble tried to investigate light spectra from distant galaxies, and his observations led to evidence that the Big Bang could be acceptable as one theory which explains the origin of the universe. So, Edwin Hubble investigated the light spectra emitted from a large number of galaxies using what we call the Hubble telescope. And his observations showed that the lines in the emission spectra from distant galaxies show an increase in wavelength. In other words, the wavelength of the spectral lines was increasing or had increased. That's what we call redshifted. So Edwin's observation showed that the wavelength of the spectral lines in light coming from distant galaxies is redshifted. And then you must be wondering how Hubble investigated the motion of distant galaxies. But if you have already studied quantum physics, you remember we have mentioned, or you will mention what we call the spectral lines that I've already talked about. So in the laboratory, Edwin knew where several spectral lines in light which is passing through, say, hydrogen should be. And if I know that the spectral lines in light coming from hydrogen should be in this position here. Remember I said the position of these spectral lines depends on the characteristics of the material through which light is passing. If light is passing through hydrogen, we expect the same three lines, for example. So Edwin Hubble knew where these lines are supposed to be. But when he observed light coming from distant galaxies using a very powerful telescope, having known that the light must be passing through the same chemical, such as, say, hydrogen, or is passing through the same material, the same cooler layer of gas, such as helium, he noticed that the spectral lines were shifting towards one end of the visible spectrum, which is actually the red end of the visible spectrum, which means that the wavelength of these spectral lines has actually increased because red corresponds to the longest wavelength. So Hubble knew what line spectra the stars should have, but then he found out that they had been redshifted. So he used the redshifted data and then what we call the standard candle that we have already mentioned, an astronomical object whose luminosity is already known. So using the redshift to determine the velocities and using the standard candles to determine the distances of these galaxies, Hubble came up with what we today call Hubble's law. So from these measurements, Hubble formulated a relationship which we now call Hubble's law. that is the recessional speed of galaxies. His observation actually showed that v, which is the speed of the galaxy, which he determined using the redshift that we have already seen, that is delta lambda, or the change in wavelength, is equal to the fraction of the speed. So he was able to determine the recessional speed of galaxies, and using a standard candle, and L equals to, or using a standard candle where F equals to L over 4 pi d squared, where the luminosity is known for a standard candle, Hubble was able to determine the distance of these galaxies from us. And when he compared the value of V and D, his observations showed that V was directly proportional to D. That's what we today call Hubble's law. So let's explore Hubble's law. So Hubble's law states that the recessional speed of galaxies moving away from the Earth is proportional to their distance from the Earth. Now the question would be, why the Earth? Of course, Hubble was taking measurements while based on Earth, so the Earth is acting as the reference point. So the word recession in this case means to recede is to move away. The speed with which galaxies are moving away from the Earth is directly proportional to their distance from the Earth. What does that mean? Galaxies which are extremely farther away from the Earth must be moving with a higher speed. The recessional speed of galaxies moving away from the Earth, they are actually moving away because the redshift has already verified this. The speed with which galaxies are moving away from the Earth is directly proportional to their distance from the Earth. If you don't take the Earth as a reference point, then the recessional speed of galaxies away from the observer is directly proportional to their distance from the observer. So if I put this in letters, V is directly proportional to D. If I remove the proportionality sign and introduce a constant, V will be equal to H naught times D, where, of course, V is going to be the speed of the galaxy, the recessional speed of the galaxy, or the recessional velocity of the galaxy. D is going to be the distance between the galaxy and the Earth, and H naught is going to be called the Hubble's constant. H naught is going to be called Hubble's constant, which is many times called the rate of expansion of the universe. That is the rate at which the universe is expanding. One important thing you need to notice is that I have not mentioned stars, have not mentioned any other object, but I've mentioned the galaxy because Hubble applied this to only galaxies because these were bigger, the distances were large enough for this law to be valid. That's why I'm saying Hubble's law only applies to distant receding galaxies. Distant. If we apply Hubble's law to our own galaxy, the distances involved are still smaller and the speeds involved are still smaller. We may not observe any changes for smaller distances within our own galaxy. So I am saying we should never apply Hubble's law to any object within the Milky Way galaxy, which is our own galaxy. Every time we apply Hubble's law, we are actually referring to objects in other galaxies, or we are referring to distant galaxies. That's why in the law we say the recessional speed of galaxies moving away from the Earth is proportional to their distance from the Earth. That's what we call Hubble's law. Of course, if V is directly proportional to D, that means if we sketch a graph of speed or velocity against time, against distance, we would expect a graph of this nature. So this is a scatter graph from results obtained by Hubble. Each dot is representing a galaxy. Each dot here is going to be representing a galaxy. And this is exactly what happened when Hubble carried out his experiment or made his observation. And The pattern in which these dots are arranged themselves was actually giving us a line of best fit. So we could draw a line of best fit through these through the data obtained for the different galaxies. And a straight line, of course, would indicate that v, the recessional speed v, was directly proportional to d. So that is a straight line, which means v is directly proportional to d. What does the gradient stand for? So the gradient of this straight line, because we notice that v is equal to h naught times d, that means if I find a gradient of this straight line, the gradient of this straight line is going to be the constant, which we call Hubble constant, that is h naught. So the gradient of the straight line is equal to the, Hubble's constant h naught. But then you may ask yourself, why was the data scattered? This graph here is actually giving you a picture of what Hubble's results looked like, and the results were scattering around the line of best fit. What is the significance of this scattering? Why were the results scattering? From your AS knowledge, you know that the scattering means there are random errors. So there must have been random errors according to what Hubble's results were showing. So we believe that there were random errors in taking these observations. So that is Hubble's law. So to sum up that graph, from the above equation and the graph, we conclude that the farther away a galaxy is, the faster its recessional speed. In other words, galaxies which are far away from us, they must be having a very high speed. The faster objects are from others, the higher the speed, the higher the speed they are moving with. Then the straight line of best fit through the origin and the gradient of the graph of the recessional velocity against distance is equal to the Hubble's constant. The straight line of best fit passes through the origin, which automatically satisfies the saying that v is directly proportional to d. When v is 0, d is supposed to be 0. Now the question is, when was d 0 and v being 0? That will take us to the Big Bang, the beginning of everything, and the origin of the universe. However, before we reach there, the constant h naught is called Hubble's constant, which we have already said it is going to be the gradient of the graph. And of course, experiments have shown that this constant is approximately 2.4 times 10 to the power of minus 18 per second. Of course, you don't need to remember this constant here. Many times you'll calculate it. And if not, you may always be given the constant if it is needed to be used in calculations. So I also talked about why the data was scattering as indicated by the previous graph. So the scatter of the data shows considerable uncertainties, which were actually random errors. We know that random errors cause a scattering of data around the line of best fit, while systematic errors would cause the average value to either be above or to be below, but not at the same time. So the scattering was because of random errors during maybe the observations. Okay, so that is Hubble's law. The recessional speed of galaxies moving away from the Earth is directly proportional to their distance from the Earth. So having seen that the straight line goes through the origin, then we should think about the beginning of everything. And this takes us back to the age of the universe. When did it start? When did everything start? That's now the origin of the universe. When did it start? When did everything start? And maybe, when was V 0? When was V 0? The beginning of everything. When was V 0? Okay, so if if the galaxies are moving away from each other, then they must have started from the same point at some time in the past. If galaxies are moving away from each other, and the recessional speed of the galaxies is directly proportional to their distance from us, if they are moving away, then where did they start from? So we can argue that if they are moving away from each other, then they must have started from the same point. And if this is true, the universe likely began in an extremely hot, dense, singular point, which subsequently began to expand very quickly or rapidly. And as it started to expand, it is still expanding up to today because we are agreeing that uh, all objects and galaxies are moving away from each other. So the universe must have started from the same point, which we call a singular point, which was extremely dense and hot, and subsequently or rapidly started to expand tremendously. And by the way, this idea is what we call the Big Bang theory. This idea is what we call the Big Bang theory. There is already evidence. Number one, we have mentioned that there was a redshift of galaxies because the wavelength of spectral lines in light coming from distant galaxies was redshifted. Number two, we have already seen, according to Hubble's law, the universe is expanding. So if there is a redshift, which is also evidence of the expanding universe, then why can't we agree that the expansion started from the same point, which we call the singular point? So, the redshift of galaxies and the expansion of the universe are now some of the most prominent pieces of evidence to suggest this theory, to suggest that this theory is true. Of course, there are other evidences such as the microwave background radiation. The microwave background radiation, we have dark energy. Dark energy, you can talk about dark matter, and so on and so forth. But this will be mentioned for those doing OCR, modeling of physics. You will mention these ones later on. But for those doing Cambridge, we shall not mention cosmic background radiation or the dark energy and dark matter. But the redshift and the expanding universe is evidence that the universe must have started from the same point and started expanding, which expansion is explained by the redshift in the wavelength of the spectral lines. So the data from Hubble's law can now be extrapolated back to the point that the universe started expanding. That is what we call the beginning of the universe or the beginning of everything. This is true if we assume that the receding speed has never changed. So the speed with which a galaxy is moving away from galaxies are moving away from each other has never changed. If we can assume that, then we can trace back when everything started. And remember, we have already said the recessional speed v is equal to h naught times d. That is according to Hubble's law. And remember, time is distance divided by speed. So if time is distance divided by speed, and we consider a galaxy which is at a distance d, and it is moving at a speed v, which speed v is h naught over d, it means the time t when this expansion must have started is going to be 1 over h naught. The time t when the expansion started is most likely going to be 1 over h naught. And by the way, if I know the Hubble's constant, then I can estimate the age of the universe. So we can estimate we can estimate the age of the universe by simply using the Hubble's constant. So what we are saying is the age of the universe is actually the reciprocal of the Hubble's constant. The age of the universe is simply going to be the reciprocal of Hubble's constant. And of course, if we substitute the Hubble's constant, experiments or estimates give the age of the universe to be around 13 to 14 billion years. For example, if I use the Hubble's constant as 2.8 times 10 to the power of minus 18, when I get to 1 over 2.8 times 10 to the power of minus 18, the age of the universe is going to be approximately between 13 to 14 billion years. So the age of the universe is approximately 13 to 14 billion years. However, there is still some discussion about the exact age of the universe. Therefore, obtaining accurate measurements for the Hubble constant is still a top priority for cosmologists. So, the reason as to why the age of the universe is still an estimate is because Hubble's constant is not really accurate. Astronomers believe there is still a problem with Hubble's constant because of the too much scatter of data, because of the too much random errors involved in obtaining information. So because Hubble's constant is not very accurate, then the exact age of the universe is still a mystery, but astronomers believe it should be between 13 to 14 billion years. So this leads us to the Big Bang Theory. The Big Bang Theory also makes you think that everything around us, including ourselves, was created during the Big Bang. Could we therefore suggest that we all have the same age? That can't be true. If everything else started as a singular point as suggested by the Big Bang, and it tremendously started expanding as different objects, galaxies, and everything else, including matter, started moving away from each other, could it be that we all started at the same point at the same time, therefore we could be the same age? That is still a question which cosmologists have not yet answered. So, the question cosmologists cannot even answer is why the Big Bang happened in the first place. There are lots of thoughts and theories, but nothing that can be tested. We can't test anything. We can't test anything to prove that the Big Bang is really final and cannot be disputed. Even though we have evidence of the redshift, it's not enough evidence for us to conclude that actually the Big Bang is conclusive and final. So there are a lot of thoughts and several theories which have not yet been tested, but astronomers and cosmologists are doing everything possible to verify and prove to the universe, to the world, that the Big Bang should be accepted. A few things we need to note here. Number one, another evidence for the Big Bang theory worth mentioning is the temperature of the universe itself. We believe that as the universe started expanding, the density of the universe started decreasing. And during the expansion, the universe started cooling. So we believe that today's temperature is as a result of the Big Bang and the expansion of the universe, which has led to cooling. Theories predicted that the current temperature of the universe should be about around 2.7 Kelvin, but data collected have shown that the peak intensity of electromagnetic radiation coming from all directions of space occurs at a wavelength of about 1 millimeter, that is microwaves. And if you recall, Wien's displacement law, where we said that lambda max is equal to a constant around 2.9 times 10 to the power of minus 3 divided by the temperature. If the data collected has shown that the peak intensity of electromagnetic radiation coming from all directions of space occurs at a wavelength of about 1 millimeter. So it means if lambda is 1 millimeter, then T is going to be approximately 2.9, which is approximately 3 Kelvin. So it's like the temperature of the universe is supposed to be approximately 3 Kelvin. But theories predict that it should be about 2.7 Kelvin. So according to Wien's displacement law, the graph of intensity against wavelength shows that the above data corresponds to about a temperature of about 3 Kelvin from that simple calculation which I've just done here. So the universe is actually cooling according to the Big Bang. Ignore the global warming taking place in different parts of the universe. The universe is supposed to be cooling because it started as a very dense, a very small, dense, hot, singular point, and which tremendously started expanding. During the expansion, we expect that as the density decreases, the universe should also be cooling, as predicted by the Big Bang. In summary, in summary, when someone talks about the Big Bang, this person is referring to the idea that the universe started as a hot, infinitely dense, singular point. The universe started as a hot, when I say infinitely, it means the density was infinite. It was very large. It was infinity. The Big Bang is the idea that the universe started as a hot, infinitely dense, singular point, which tremendously began to expand very rapidly. The expansion continues as evidenced by the redshift. Up to today, we believe that the universe is still expanding. But during the expansion has led to the cooling, resulting into the current temperature of very close to 3 Kelvin. During the expansion, the universe started cooling, and because the expansion is still continuing, expect that the universe is still cooling down. So the universe as a black body is associated with microwaves at this temperature of 3 Kelvin with the same intensity in all directions. So microwaves observed, or the background microwave radiation observed in the universe in all directions, corresponds to a temperature of approximately 3 Kelvin. So when someone talks about the Big Bang, you should be referring to a hot, infinitely dense singular point which started expanding, and as it started expanding, the temperature started decreasing. There is evidence of the expanding universe as given by the redshift or the Doppler redshift. Let me give you a sample question. Sample question number one. The examiner may ask you, how do cosmologists determine that the universe is expanding? How do you come to know that the universe is expanding? I think that one we have already mentioned. The redshift is evidence that the universe is expanding. But how will the cosmologists know that the universe is actually expanding? So, what cosmologists do would be to simply analyze or examine spectral lines in light coming from distant stars, and then compare with the known values in the laboratory. And of course, the comparison shows that the wavelength of the spectral lines is redshifted. Therefore, cosmologists will simply conclude that the universe is expanding. So, I am simply saying the wavelength of spectral lines of light from distant stars are observed to be greater than their known values in the laboratory. So if the wavelength of spectral lines of light from distant stars is greater, then why is it greater? Of course, being greater, that's what we call the redshift. So this redshift shows that stars in distant galaxies are moving away from the Earth. Hence, the universe is expanding. Or the galaxies in which these stars belong are moving away from the Earth. Hence, the universe is expanding. So that is how astronomers are able to tell that the universe is expanding. Sample question number 2. Explain how Hubble's law, that is, of course, Hubble's law, that is V is directly proportional to D, and the idea of the expanding universe, which is, of course, verified by the redshift. And if the universe is expanding, it means everything else is moving away from each other. All objects are moving away from each other. How do these two, the expanding universe and Hubble's law, lead to the Big Bang theory of the origin of the universe? So if the universe is expanding, then it means all parts of the universe are moving away from each other. All objects are moving away from each other. Then according to Hubble's law, because v is directly proportional to d, it means the more distant objects must be moving far away, must be moving with a higher speed or with the highest speed. The farther an object is, the faster it is moving if we consider Hubble's law. And then if they are moving, then why can't we believe that they started from the same singular point as proposed by the Big Bang theory? So what I'm saying is very simple, that if the universe is expanding, then all parts of the universe must be moving away from each other. And from Hubble's law, the more distant objects must be moving away faster because v is directly proportional to d. And if they are moving away, then matter must have been close together in the past. Matter must have been close together in a very dense singular point in the past, as proposed by the Big Bang theory. Because the Big Bang theory predicts that the universe started from a singular point in the past, which tremendously started expanding. And during the expansion, the temperature of the universe started cooling, and it continues to cool to cool today. There's evidence for the expansion as given by the redshift. So that's what we call the Big Bang theory. Okay, let's do a few examples and we conclude this unit. Example number 1. These are just further examples. A galaxy is found to be moving away, so it is redshifted. Light is redshifted with a speed of 2.1 times 10 to the power of 7 meters per second. That is the recessional speed. The galaxy is at a distance of 9.5 times 10 to the power of 24 meters from the Earth. Assume that the speed of the speed has remained constant. What is the age of the universe? So every time we consider v equals to h naught times d, every time we try to estimate the universe, we assume that the recessional speed of a certain galaxy has remained constant. So we want to find the speed of the universe, or the age of the universe. So remember, time is equal to the distance divided by the speed, which distance is d and the speed is h naught divided by d. So the time, which is the age of the universe, is going to be, it's actually supposed to be 1 over h naught. But I will simply just use distance, which is given as that, and the speed as that, to find the age of the universe. I may not need to use, because I don't have Hubble's constant, I'll just use this. So this is going to be 9.5 times 10 to the power of 24 divided by 2.1 times 10 to the power of 7. And I'll just try to press my calculator. So this is giving me the time here as 4.52 times 10 to the power of 17. This is seconds. We want to estimate the age of the universe in years. So I have to change this to years. So the time is going to be equal to 4.52 times 10 to the power of 17 divided by. So 1 year is approximately, I'll take 365 days. And 1 day is 24 hours, and 1 hour is 3,600 seconds. So I'll divide this by 365 times 24 times 3,600. So the answer here is going to be in years. I'm changing seconds to years. So I'll press my calculator. So this is giving me a 1.43 times 10 to the power of 10 in years. So this is approximately 14.3 times 10 to the power of 9 years. Of course, 10 to the power of 9 is 1 billion. So this is approximately 14.3 billion years. So every time we try to estimate the age of the universe, the answer will be between 13 to 14 billions. Every time we try to estimate the age of the universe, the answer will be between 13 to 14 billion years. So that is the estimate age of the universe. So the age of the universe is approximately 14.3 billion years. Example number 2. Light from a distant galaxy is passed through a diffraction grating. The figure below shows the part of the spectrum of light that shows a strong hydrogen alpha emission line. So it is an emission line, which means transition is from a higher energy level to a lower energy level. So the electron is making a transition from a higher energy level to a lower energy level. It is giving out a photon. If it is an absorption line, then the electron would be moving from a lower energy level to a higher energy level. In other words, the electron will be absorbing a photon. So in quantum physics, you know the difference between emission and absorption. Emission, the electron gives out a photon. So it moves to a lower energy level, resulting into this hydrogen alpha emission line. If it was an absorption, the electron absorbs a photon, which would result into an absorption line, which would be actually a dark line. So the figure shows how the part of the spectrum of light that shows a strong hydrogen alpha emission line. State how an emission line spectrum is produced. Of course, I've already explained how an emission line is produced. An electron makes a transition to a lower energy level. That means it gives out a photon. So it loses energy and emitting a photon or electromagnetic radiation. That's what results into, or that's why we would see or notice a hydrogen alpha emission line or an emission line. Then part 2, state an adjustment that could be made to the experimental arrangement that would space the lines more widely. So if we want to space the lines more widely, the spectral lines can be studied by a diffraction grating because the light must be passed through a diffraction grating to be able to separate the wavelength. And remember from your AS knowledge, for a diffraction grating n lambda is equal to d sine theta. So if you want the spectral lines to be more widely spaced, in other words, we want theta to be greater, we must change n of these. We must change, for example, we can change this one here, which is d. That is the grating, the separation of the slits in the grating. So we can increase, because sine theta is inversely proportional to d. Sine theta is inversely proportional to d. So because I want the spectral lines to be more widely spaced, I must increase the angle. So if sine theta is to increase, this must be decreased. So we are going to reduce the grating separation. But also, by the way, we can increase the distance between the grating and the screen. If this distance is increased, if the distance between the grating and the screen is increased, because sine theta can also be measured from on a screen, you can also measure theta by using the opposite over the adjacent. Opposite of adjacent is tan. I can find the angle theta from tan theta is equal to the distance on the screen, x, over the distance from the grating to the screen, which is capital D. So if I change D, it means if I increase D, then of course Of course, I think the theta, if I increase d, then theta is going to increase. Therefore, there are two ways of doing this. You reduce the separation of the grating, which is small letter d, or you increase the distance between the grating and the screen. Because to analyze the spectral lines, light must be passed through a diffraction grating, which you mentioned in AS physics. Okay, example number 2 is still continuing. In the laboratory, the wavelength of the hydrogen alpha emission line is 656.3 nanometers. Use the figure to determine the recessional velocity of the galaxy. So of course here we are going to use the difference in wavelength is equal to V divided by C. So V is going to be equal to the change in wavelength divided by lambda times C. The change in wavelength in the laboratory, this is the known value in the laboratory. But then from the distant galaxies, I think this line is corresponding to, what is that, center. So 661.5. So this is 661.5. So this is going to be 661.5 minus 656.3 divided by 661.5, then times 3 times 10 to the power of 8. So this gives us the recessional speed. I'll check my calculator. Okay, so from my calculator, I've got the recessional speed as being 2.4 times 10 to the power of 6 meters. So the recessional speed is 2.4 times 10 to the power of 6 meters. Then part C suggests why hydrogen spectral lines play an important role in determining the redshift of galaxies. Of course, we said the most important sources of light in all galaxies are the stars. The fuel for the stars to produce their light and heat or energy is hydrogen and helium. So we know that hydrogen is in abundance in all stars which are found in all the galaxies. So the major important region is that the relative balance of hydrogen in stars, or the abundance of hydrogen in stars, is very high. So relative abundance of hydrogen in all stars is very important here. It is in abundance. Okay. Part D, it is still continuing. Light from a similar star is viewed in a galaxy farther away. The star is part of a pair of stars which orbit a common center of mass. Describe and explain how the equivalent spectrum may appear. So there's light from a similar star, but it is viewed from a galaxy which is farther away. That means it's going to be more redshifted. It is farther away, so it is going to be more redshifted. Because if it is farther away, if you look at this expression here, delta lambda over lambda being equal to V over C. So it is going to be farther away. If it is farther away, it is more redshifted, and therefore it is having a higher speed. It is moving faster. And since it is more redshifted and is moving faster, then the line is going to be less intense. So describe and explain how the equivalent spectrum might appear. So number one, I'm saying the line is going to be less intense, or the lines are going to be less intense. Describe and explain how the equivalent spectrum might appear. So it might be less intense because the galaxy is moving faster, and therefore greater or longer wavelength. The spectral lines have a longer wavelength. There will be a periodic shift in wavelength. If the plane of orbit is in the line of sight, of course I'll leave out this one because it is more advanced. It is for only those doing OCR are the ones who will understand this. There will be a periodic shift in wavelength if the plane of orbit is in the line of sight. Let's concentrate on the line being intense because the galaxy is moving faster. Because it is farther away, it is more redshifted. And if the redshift is more, it's only because it's moving at a faster speed in comparison to the one we have considered previously. Okay, example number 4. I think this one is easy. Students can try out this. An emission spectral line is measured in the laboratory to have a frequency of 7.3 times 10 to the power of 14 hertz. Determine the wavelength. Determine the wavelength of this spectral line in the laboratory. Determine the wavelength of the spectral line in the laboratory. Part 2, determine the observed wavelength of this same spectral line in the spectrum of a galaxy moving away from the Earth at a speed of 11 meters per second, 7% of the speed of light. I think this is an easy question, but is it continuing? The spectrum of all distant galaxies is redshifted. State and explain what you can deduce about the universe. Of course, redshift. From the redshift, we can deduce that the universe is expanding. As simple as that. Maybe just to give you a clue on this, on part A, determine the wavelength of the spectral line in the laboratory. So we have the frequency here. So we know that the apparent change in frequency is equal to the apparent change, the fractional change in wavelength, which is equal to V over C. So they have given us the frequency in the laboratory, and they want us to determine the wavelength. That one I will just simply use a lambda equals to C over F, which will be 3 times 10 to the power of 8 divided by F, which is 7.3 times 10 to the power of 14. I'll just press my calculator. 3 exponent 8 divided by 7.3 exponent 14. So this is simply 4.11 times 10 to the power of 367 minus 7 meters. So the wavelength is 4.11 times 10 to the power of minus 7 meters. Then determine the observed wavelength of this same spectral line in the spectrum of a distant galaxy. So this one is the observed in the laboratory. And we want to find the observed wavelength when the speed is 11 megameters per second. So from this equation here, we know that the observed wavelength, lambda observed, minus the wavelength in the laboratory, which is 4. I want to change this to, okay, let me just leave it as it is, 4.11 times 10 to the power of minus 7 divided by 4.11 times 10 to the power of minus 7 should be equal to V over C, where V is 11 times 10 to the power of 6 mega divided by 3 times 10 to the power of 8. So I'm just going to press my calculator to find lambda naught. So I'll say 11 exponent 6 divided by 3 exponent 8. Then I'll multiply this by 4.11 exponent minus 7. Then I'll take the minus 4.11 times 10 to the power of minus 7 in the brackets to the right hand side. So I'll say plus 4.11 exponent minus 7. So the observed wavelength is 4.3 times 10 to the power. Okay, let me write 3 significant figures because this was 4.11. So it is 4.26 times 10 to the power of minus 7 meters. So that is the observed wavelength, 367. Okay, so note that in this bracket here, I was getting delta lambda, the change in wavelength, which is the same as the observed wavelength from a distant galaxy minus the wavelength in the laboratory. That's what I've done there. Then they want us, you can now try this one, 7% of the speed of light. I've already used 11 megameters per second. You can check this one. I'll just press my calculator and put the answer here. So 7% of the speed of light, that is 0.07 times 3 exponent 8 divided by 3 exponent 8 times 4.11 exponent minus 7 plus 4.11 exponent minus 7. So the answer here is going to be 4 actually it is approximately 4.40 times 10 to the power of minus 7 meters. Same method, same process. Okay, that is example number 4. Then example number 5. The recessional speed v against distance d for some galaxies is shown besides. Okay. Deduce the Hubble's constant. Deduce the Hubble's constant. Remember from what we have just covered or what we have just said, Hubble's constant is actually the gradient of a graph of v against d. So I'll just find the gradient here. So I have to look for, the graph goes through the origin, so I'm just going to look for a convenient point such as, I hope this is convenient enough. I hope this is convenient enough. Because the graph goes to the origin, I'll just use this point here to find the gradient. So Hubble's law or Hubble's constant is equal to the gradient. Hubble's constant equals the gradient, which is going to be 6.0, of course, minus the origin times 10 to the power of 6 divided by, because I'm using v equals h naught times d, where h naught is the gradient. So divide this by, this is going to be 1.5, 2.1.2.3. So this is going to be 2.3. This is 2.3 times 10 to the power of 24. So just press my calculator. 6 exponent 6 divided by 2.3 exponent 24. So I am getting 2.6 times 10 to the power of minus 18. Of course, this is per second. Yeah, I think this is per second because we have meters per second divided by meters. So that is per second. So every time you calculate Hubble's constant, the power of 10 is going to be approximately minus 18. Every time it will be minus 18, Hubble's constant. The power of 10 will be minus 18. Okay. The Big Bang occurred some 14 billion years ago. Estimate the farthest distance cosmologists can observe. So this is going to be the time for which observations have been taken. And because cosmologists rely on the redshift to estimate to explain the expansion of the universe, then we shall use the speed of light as the speed. So from speed, I mean distance equaling to the speed multiplied by the time, then we can see the farthest distance cosmologists can see would be the speed of light 3 times 10 to the power of 8 times the time, which is 14 billions, that is 14 times 10 to the power of 9, that is in years, times 365 to change it to days, times 24 hours, times, because the speed of light is in meters per second, so I'm trying to change the time to seconds, so times 3600. So this is the time, this is to change the time in seconds. So I'll press my calculator to find the answer. Okay, so number of days in a year, hours in a day, seconds in an hour. So this is giving me 1.32 times 10 to the power of 26 meters. So this is the farthest astronomers can see. That means if we have the distance from the Earth to other points is farther than this, perhaps astronomers are not able or will never be able to see such distances. Okay, example number 7. An astronomer has determined the surface temperature of a white dwarf star to be 7,800 Kelvin and its radius as 8.5 times 10 to the power of 6 meters. Calculate the luminosity of this star. So they have given us the temperature of the star and they have given us its radius, and we want to find the luminosity. Of course, here we are now going to just use Hubble's law. Not Hubble's law, we are going to use Stefan Boltzmann's law. L luminosity is equal to 4 pi r squared times sigma times t to the power of 4. So this will be 4 pi times the radius, which is 8.5 times 10 to the power of 6, but this should be squared, times sigma, which is 5.67 times 10 to the power of minus 8, that is Stefan Boltzmann's constant, then times the temperature, which is 7800 raised to power 4. So I'll just press my calculator. 4 pi times 8.5 exponent 6, but this is squared, times 5.67 exponent minus 8 times 7800 power 4. So the luminosity which I'm obtaining here is 1.91 times 10 to the power of 23 watts. So the total radiant power emitted by the star is going to be 1.91 times 10 to the power of 23 watts. I hope I pressed this correctly. Let me try to check again. 5 times 8.5 exponent 6, but this is squared, times 5.67 exponent minus 8 times 7800 power of 4. So that is the total radiant power emitted by such a star. Okay. Example 8. The surface temperature T of a star depends on the wavelength lambda max at the peak intensity of the emitted radiation from the star. The T against lambda max graph for a cluster of stars in our galaxy is shown besides. Use the graph to show the way that Wayne's displacement law is obeyed. Estimate the surface temperature of a star. with lambda max equal to 400 plus or minus 10 nanometers. In your answer, include the absolute uncertainty. Okay, so for Wayne's displacement, remember we say that lambda max times t should be equal to a constant. So I should check this for three values of lambda and t. So I'll check for three values of lambda and t. To see if it is a constant, I'll start with this one here. So here this is, I think each of this is 10. So this is 1, 2, 3, 4. So that is 640 nanometers. And this is, each of this on the vertical is, I think this is 4,500. So starting with, I have that 640 nanometers times 4,500 equals to, let me see what, I've not changed the units, I just want to know if it is a constant. So 640 times 4,500, this is equal to 2.88 times 10 to the power of 6. Whatever units, I don't need the units, but I will write there the units, nanometers times Kelvin. Then let me check again at another point to see if it is still the same. I will check this point here. So at that point I have 790. That is the wavelength times. So this is 500, 600, 700, 3,700. This one is 790 against 3,700. So let me check my calculator. 790 times 3,700. So this is giving me 2.92 times 10 to the power of 6 nanometers times Kelvin. I can check the third one. Let me check. There's this one here, this point here. So this is 900 and I think this is 940. This is against 3,100. So 940 times 3,100. So 940 times 3,100. So this is giving me 2.91 times 10 to the power of 6 nanometers Kelvin. So the question is, use the graph to show that Wayne's displacement law is obeyed. So when I round off this to two significant figures, this is approximately 2.9 times 10 to the power of 6, 2.9 times 10 to the power of 6, 2.9 times 10 to the power of 6. Hence, I can say lambda max times t is equal to a constant. Therefore, it is obeyed. So for such questions which ask you to show that a law is obeyed from the graph, you should make at least 3 attempts. At least 3 attempts and round off to a certain significant figure and conclude that it is obeyed. If I round off to, I can still argue that it's not obeyed if I consider 3 significant figures. So, but to two significant figures, it is obeyed. But to more than two significant figures, the values are different. So we could say, or someone would also argue that it's not obeyed. But if you want to say it is obeyed, you must round off to two significant figures before you conclude that it is obeyed. To two significant figures, lambda max times t is equal to a constant, hence it is obeyed. But if you don't want to say it is obeyed, then you can consider this number of significant figures. Then estimate the surface temperature of a star, lambda max equals to 400 plus or minus 10 nanometers. In your answer, include the absolute uncertainty. So I can take the first one. Remember, lambda max times t is equal to a constant, so I'll say 400 nanometers times the unknown temperature is equal to a constant, which I will take 2.8. I'll take 2.88 times 10 to the power of 6. I've just taken the first one. So the nanometers, of course, is going to cancel because this is nanometers times Kelvin. So nanometers has cancelled. So it means T is going to be equal to 2.88 times 10 to the power of 6 divided by 400. So the temperature is going to be 2.88 exponent 6 divided by 400. So this is approximately 7,200 Kelvin. So now when lambda max is 400, then the temperature is going to be approximately 7,200. You can't see this from the graph, of course. Okay. Then in your answer, include the absolute uncertainty. So we need to find the absolute uncertainty. So because lambda, or because t is equal to because t is equal to a constant divided by lambda max, because t is equal to a constant divided by lambda max, and lambda max has an absolute uncertainty of 10 nanometers. I can find the absolute uncertainty from the graph here. Let me check from the graph. On the wavelength scale, the absolute uncertainty is going to be the value of one small division, which is, let me see, one small division, that is 600 for, I think one small division is 10. So the uncertainty on the x-axis is 10 nanometers also. So it's like we are dividing k, which k has wavelength multiplied by temperature. Wavelength multiplied by temperature. Of course, if I take k to be a constant, then I'll just consider the absolute uncertainty in lambda max. So this is still simply going to be absolute uncertainty in the reciprocal is actually equal to the fraction uncertainty. So this is going to be the absolute in t is going to be equal to the absolute in lambda max, which is 10, divided by lambda max, which is 400. That is the fractional, then times t, which is 7,200. So that is going to be times 10 divided by 400, which is approximately 200 to, it is approximately 200 to one significant figure. So the answer would be written as 7200 plus or minus 200 Kelvin. So that is the absolute and the value of t with this absolute uncertainty. Okay, I think this is almost the last question. Oh, there's one more. Light from a galaxy is passed through a diffraction grating. The diagram shows part of the emission spectrum. The strong emission spectral line has wavelength 620 and 62. Calculate the energy of a photon of wavelength 662. Of course, for energy of a photon, we know that this is from quantum physics. For energy of a photon, we know that energy, I don't have enough space, so I have to look for where to do this from. So we have that energy is equal to hc over wavelength, and this is going to be 6.63 times 10 to the power of minus 34, then times 3 times 10 to the power of 8 divided by the wavelength, which is 662 times 10 to the power of minus 9. So I have to press my calculator. 6.63 exponent minus 34 times 3 exponent 8 divided by 662 exponent minus 9. So the energy here in joules is 3.0 times 10 to the power of minus 19 joules. In part 2, explain how a spectral line is produced by electrons within atoms. Of course, we now know how spectral lines are formed. An electron will absorb a photon and makes a transition to higher energy level. This is an emission spectrum. So an electron is therefore going to emit a photon. So the electron emits a photon and moves to lower energy levels, thereby um, resulting into an emission line. Okay, so for emission, the electron gives out a photon. It moves to a lower energy level, as you mentioned in quantum physics. If it is absorption, the electron absorbs a photon. This is normally in cooler layers of gases. So an electron absorbs a photon in cooler layers of hydrogen gases or in cooler layers of hydrogen and makes an upward transition or a transition to a higher energy level. For emission, the electron emits the photon and moves to a lower energy level. That is what we call de-excitation in quantum physics. Okay, so I've explained how it is formed. That one I will not repeat it. In the laboratory, the same spectral line has wavelength 656. So this is the actual wavelength, the known wavelength in the laboratory. Calculate the speed of the galaxy. So we know that the change in wavelength over the wavelength in the laboratory is equal to V over C. So V is going to be equal to the change in wavelength is 662 minus 656 divided by the wavelength in the laboratory, which is 656 times 3 times 10 to the power of 8. So 662 minus 656 divided by 656. 662 minus 656, 656. Then times 3 exponent 8. So the speed is 2.7 times 10 to the power of 6 meters per second. Then state the direction of the of travel of the galaxy. So you notice that the wavelength of light from the galaxy is longer than the wavelength, the known value in the laboratory. So this is moving away. It is already shifted. Set and explain what the wavelength of the same spectral line would be for a much more distant galaxy. The wavelength. So for a much more distant galaxy, because V is directly proportional to D, because the distance is bigger, V is going to be bigger. And remember, V is directly proportional to the change in wavelength. So the change in wavelength is going to be greater. And if the change in wavelength is greater, yet the known value in the laboratory remains 656, it means the wavelength, because this is going to be the observed wavelength from the galaxy minus the known value, which known value is constant. But because the change in wavelength is bigger, then it means lambda naught is going to be bigger, so it is going to be much greater, much longer. So the wavelength of the same spectral line is going to be much longer for a more distant galaxy. Okay, I think this is now for you to try out. Define a radiant flux intensity. We have already defined this. State the relationship between radiant flux intensity F and the distance d. We have already done that. Neptune is the farthest known planet from the Sun in the solar system. Its distance from the Sun is 30 times greater than the distance of the Earth from the Sun. The radiant flux intensity from the Sun at Earth is 1400 watts per meter squared. A space probe is close to Neptune. Calculate the maximum radiant power received by an instrument of cross-sectional area 1 centimeter squared on the space probe. So the space probe is close to Neptune, and therefore using F equals to L over 4 pi d squared for the two objects, you should be able to find the maximum radiant power received by the instrument. In other words, you must find F at the space probe. I think that one you should be able to try out. And that is the end of Astrophysics.